Here we're looking at track test data, but it would work with other types of data. So we look at different sensors on the car, different accelerations and forces on a car as it's driving around tracks. And you can see the sort of time series sensors or kind of signals that you get. So imagine if you have like hundreds of those, it's quite hard to find if one is anomalous. And so the way you train a model, I'll just edit it here. You load your data, then you specify what is the column that defines time, so the time column, then specify which column is going to identify different tests that you're doing. So it could be, I don't know, different labs, different brands, but it could be different aging tests, different cells or anything. And then select all the channels that you want to evaluate. And then you have some parameters that you can tune. So some parameters to improve the reconstruction of the signal. So you improve your model to get a better reconstruction, and then some parameters to improve the sensitivity or tune the sensitivity of the detector to your needs. So you train this model, you get a loss curve that's going to show you how quickly and how well your model is learning to reconstruct the nominal data, and then you can consume it. And so that's the heat map that we showed before. You can see in this case that there's like 3 quite severe anomalies. So here we're looking at the severity of anomalies in this map. And then when you click on one of them, below you have the raw signals. So here, if I focus on the actual data, in this case, you can see that's what was measured. This is what the anomaly detector expected. So it's saying that's what I'm expected as a signal. And therefore, you can see here towards the end, there's a high anomaly score because there starts to be a deviation between what I expected and what I actually measured.
So this might be a good area to talk a bit more about the anomaly score, because it appears that it's not just a difference between the acquired and expected data, because looking at kind of the score early in this waveform versus later seems to be pretty different. What's going on there?
Yeah, that's a good point. Actually, you can see here, for example, that between the actual data in blue and the predicted or expected signal in green, there's quite a high difference, but somehow the anomaly score is low. While at a later stage, you might have regions with maybe a similar sort of difference or error in the reconstruction, but the anomaly score is really high. And that comes back to what I mentioned earlier when I was saying we noticed that just looking at the difference or the error was not enough. And so here is using, obviously, this difference in reconstruction, but is not just using the difference at each point, is looking at it through different kind of windows and different sort of sensitivity. So there's a lot of different aspects that from this reconstruction generates a score. And as you say, you can see here, it's basically understood that this is actually not really anomalous. Even if my reconstruction is not perfect, I'm not flagging this as anomalous. While in a region like here, where the error is not too high, it looks like I'm still already part of a drift, and I'll still flag that as a higher anomaly. So it's a good illustration of how calculating an anomaly score and not just looking at the error can make a big difference in your outcome. Yeah, that's a good point. So I'm just going to click on a few more. So here, for example, there's another one that seems quite anomalous for this maneuver, acceleration Y. You can see the score here, 0.9999. So I click on it, and in a few seconds, I'll get another kind of visual here of the raw signal. That's the one I showed before, where you can see here that the sensor is kind of dropped out there, and that wasn't expected. And as a result, the score is going to be really high in this region. And that's well captured by the kind of severity here. It's quite severe, even if it's not really prevalent across the test. Now what I can do as well is change the way I look at the anomalies, and instead of looking at the severity, I look at the prevalence. So what are the anomalies that are prevalent across the test? And that will change a bit the map. You can see here is less red, basically, because a lot of these anomalies, if they occur here or there, they will be diluted across the whole test. But there's one that remains quite prevalent, so we can actually look at this one here. And again, we wait a few seconds, the signal is going to be updated down here. And what we have here is it's basically a sign inversion. So here, this is what was measured, and this is what was expected. So the signal, the anomaly detector is saying, well, looks like you always have the opposite of what I'm expecting. And as a result, the anomaly score is high a lot of the time through the test. And that's what makes it really prevalent. It's not just localized, it's really anomalous across the whole test. So that's how you set up and how you use anomaly detection in the platform. So I've done this in a notebook in the Monolith platform. But then when you have that done, you can kind of create a dashboard from the notebook. So I have a dashboard here as an example where it's set up so that the consumer, the user, can bring a new set of data that they want to evaluate, and then wait a few seconds and get this heat map generated where they can already kind of interact with it, understand what was anomalous in a very, again, visual and interactive way. What they can do as well is that this data is not just used to be visualized, but the raw data is available as data sets. So you can do some more automated post-processing. For example, you could sort the most anomalies, kind of the highest anomaly scores by a combination of test and channel. So for example, this maneuver with car angle was the most anomaly score, and you can have the 10 most anomalous ones. You can apply thresholds. So there's a lot that you can do in addition to this visual part.
So again, for those of you that are new to Monolith, just as a reminder, the notebook that Joël was showing before is where you kind of construct your workflows with your data. And now this dashboard is more as an interactive tool where you can kind of bring the results together and share it with others. Now here, Joël, you're showing the dashboard. I guess talk a little bit about how this could be automated within your workflow, your engineering workflow.
Yeah, there's different ways to consume it, a bit like the rest of our platform. There's the sort of interactive way to do it in the platform, and a lot of people are happy to use these dashboards in a very interactive manner. You can also download the data there if you want. But then some people prefer to do that a bit more in an automatic fashion. So if you're using APIs, you could bring data, run it through the anomaly detector, retrieve the data with all the raw signals, the expected kind of values and the anomaly scores, and then do your own processing somewhere else or be notified when you reach a threshold. So that's really up to you in how you want to consume these results.